Okay, I had to end the previous video because we were almost out of time. But there's my there's my antiderivative. Again, some of the high points here, kind of going back through things. That this was pi over 12x. And we've talked about when you have a slope here, it's a linear argument. The effect of that slope when I anti-differentiate is to divide by that number. Divide is the same thing as multiplying by the reciprocal. So multiplying by the reciprocal, we get pi over 12 over pi. Then I ask myself, what has a derivative of cosecant squared? Well, the derivative of cosecant squared, the derivative of cotangent gives me negative cosecant squared. I want to end up with positive. So to compensate that I want to end up with a positive, I got to put an extra negative in there, because when I check it, when I do the differentiation, there's really two negatives there. It's going to kick it back to positive. Then e to the x. E to the x is its own derivative, so it's its own antiderivative. And then lastly, e to the 3x. The effect of that slope, linear arguments, is that I'm going to divide by it, multiply by the reciprocal, 1/3, and then e to a linear exponent always just repeats itself. Now let's make this look a little prettier. So that's 3/2 sine 2x minus 4 secant x minus 12 over pi cotangent pi x over 12 plus e to the x plus 1/3 e to the 3x plus c. And I have some room here, so I am actually going to check this. I can check this by differentiation. And you've got a few moments at the end of a test, or if it's a different time when we're having quizzes, a few moments at the end of a quiz. You got a few moments, check these things. You can check all your answers by differentiation. So now carefully differentiating these things. So 3/2 just a coefficient, just going to stay there. Derivative of sine is cosine. My angle doesn't change. Chain rule, the effect of that 2 when I'm differentiating is to multiply by it. 4 is just a coefficient, so it's just going to stay there. Derivative of secant is secant tangent. That 12 over pi is just a coefficient, so it just stays there. Derivative of cotangent is negative cosecant squared. But then the chain rule, the effect of that pi over 12, chain rule is going to have me multiply by it. And dropping down because I'm running out of room. So I'm up to here. The derivative of e to the x is e to the x. And then I'm here. That 1/3 is just going to stay there. Then e repeats, derivative of the exponent, and very technically, the derivative of that c on the end is 0. And let's make it look prettier. So we have 3 cosine 2x minus 4 secant x tangent x. Here, these two negatives cancel, the 12 and the 12s cancel, the pi's cancel. And so I have plus cosecant squared pi x over 12 plus e to the x plus e to the 3x. And if we bring down the original piece of paper where the problem was on, so there you can see the original problem and you can see my check, and they are the same. You have to be able to differentiate your answers back to the original problem. So if you got some time, check the things that you can check. This checks back. And a lot of these you'll be able to check just by looking at them. You won't necessarily have to write it down in the detail that I wrote it down. Okay. Last basic problem, and then we'll change topics. Not really, but just a little bit. Find the most general antiderivative. Okay, let's rewrite this a little bit. So that's 3 times 1 over x. I'll run out of room if I write it there, so let's write it down below. And so that's 3 times 1 over x plus 1/2 times 1 over the square root of 1 minus x squared minus 4/5 times 1 over 1 plus x squared plus 4 to the x plus 3 to the 7x. So there's still my original problem. And so this is all based on the last page of basic antiderivatives that we are given. Based on this last page here, that the antiderivative of 1 over x was the natural log of x. The antiderivative of 1 over the square root of 1 minus x squared was sine inverse of x. The antiderivative of 1 over 1 plus x squared was tan inverse of x. And also this guy here, that the antiderivative of a to the mx was 1 over m, 1 over the natural log of a to the mx. Again, not 6, or in this case, 5, not 5 pieces of new information. It's just your derivative statements turned backwards. What has a derivative of 1 over the square root of 1 minus x squared? Sine inverse x. What has a derivative of 1 over 1 plus x squared? Tan inverse. It's just your derivative statements turned backwards. So now that we reviewed that page, doing this, so my antiderivative, capital F of x, that 3 is just a coefficient. Then I ask myself, what has a derivative of 1 over x? Natural log of x. Sometimes they're going to slap absolute value around it, sometimes they're not. It just depends on how picky they are and whether they put a little comma x greater than 0. If in doubt, put absolute value around it. I'm not going to be particularly picky. And you can always click through view an example. Don't use view an example for learning things, but click through view an example, and however they answered it is the form you should answer it. So if they used absolute value, you use absolute value. The 1/2 just stays put. Then you're asking yourself, what has a derivative of 1 over the square root of 1 minus x squared? And that's sine inverse of x. The coefficient just stays there. Then you're asking yourself, what has a derivative of 1 over the quantity 1 plus x squared? And that's tan inverse. Then we get to the slightly harder ones. And again, it helps to remember the derivatives. The derivative of 4 to the x would be 4 to the x times the natural log of the base. That it repeats derivative of the exponent here is just 1, natural log of the base, times the natural log of the base. So when I anti-differentiate, because differentiation has times the natural log of the base, anti-differentiation is going to have divided by the natural log of the base, and then just the 4 to the x. Then same idea here, just with an extra thing. I'm going to divide by that natural log of 3 because the derivative statement has times the natural log of the base. So the anti-differentiation statement is going to have divided by the natural log of base, or multiplied by the reciprocal. Then that slope up in the exponent. Linear arguments, linear exponent in this case. The effect of that 7 is to give me a 1/7. That if I was differentiation, the chain rule would have me multiply by it, anti-differentiation, divide by it, and then exponentials in general repeat. And then I throw on that plus c, because they said most general antiderivative. And then I just clean it up. Actually, there's not much to clean up here. The most you would do here you could write this on towards the end. If you wanted to save a little space, you could say that that was 4 to the x over the natural log of 4. And you could say that's 3 to the 7x over 7 natural log of 3 plus c. And then again, you could check that by differentiation if you had the time and space to do so. All of these check. Now, getting better notation. This capital F of x thing for the antiderivative and this lowercase f of x for the original function, that's a little cumbersome and it's not great notation. So better notation. Let capital F of x be an antiderivative of little f of x. Then, you got this elongated s. Then the integral of little f of x dx is capital F of x plus c. So this sign right here, the integral of f of x dx, is read the indefinite integral of f of x dx. Now I wrote indefinite parenthetically because most people don't say the word indefinite. We will discuss something called the definite integral, and the definite integral has notation that makes it look absolutely like a definite integral. So most of the time people don't say the word indefinite just because when we get to the definite integral, the way you read the definite integral is different than the way you read the indefinite integral, and so you can leave out the word indefinite. But right now we'll call it the indefinite integral. The process of finding antiderivatives is either called antidifferentiation or integration. Because the process is called either antidifferentiation or integration, we will call the answers either antiderivatives or integrals, or the most general antiderivative or indefinite integral. But the point here is, so antiderivatives and integrals are the same thing. So when someone says integrate, that's the same thing as saying antidifferentiate. Someone says find the antiderivative, same thing as finding the integral, find the integral, find the indefinite integral. Antiderivatives and integrals are the same thing. So when you see this notation, when you see the integral of f of x dx, that means find the most general antiderivative, or find the indefinite integral, or find the integral, or find the antiderivative. That's going to be our notation that says find the antiderivative now, find the indefinite integral now. That's the notation that tells us to integrate, to antidifferentiate. Just like when you see find dy dx, you know to differentiate. Now when you see this, you know to antidifferentiate or to integrate. So that is called the integral sign. It is an elongated s for reasons that we will talk about later. The dx is called the differential. For now, just think of it as part of the notation. The little f of x is called the integrand. The capital F of x plus c is the most general antiderivative, or the indefinite integral. The plus c is called the constant of integration. The integral sign and the differential dx put together are the symbols that will tell you to find the antiderivative. That's our notation giving you the instructions to the problem. When it says find the integral of blah, blah, blah dx, it's saying find the antiderivative. So our previous rules about antiderivatives now become 1. The integral of mx dx is mx plus c. The integral or antiderivative constant is the constant times x. So the integral of 3 dx is going to be 3x plus c. The integral of 3 dt will be 3t plus c. The integral of 3 dy is 3y plus c. Now, I will not count off on a test. If I happen to put dy and you write 3x here, I'm not going to count off for it. Computer will. That the differential dx, dt, dy is telling you what variable they are using. I don't care. If you get it wrong, I'm not going to count off for it. Computer will. But then check. All of these are going to check by differentiation. You can check all your integration answers, all your antidifferentiation answers, you can check by differentiation. And you should get back to the original integrand. And we'll end this video and continue on in the next one.